Testing. 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 Boo, come help test. Gotta come help test, Boo. Test. Why is this? I'm gonna get no audio here. Come on. Come on. Refresh. No audio here. Okay, I'm getting some audio. Still doesn't sound great. I need to redo my microphone settings here. Right? Maybe a compressor. What about now? Testing again. Alright, maybe the compressor makes it a little bit better, but if it's no good, let me know. Welcome to another HooPost stream. We're going to be looking at TensoIR, Tensorial Inverse Rendering. So this is very interesting. I was browsing yesterday at all the CVPR papers. So CVPR is the kind of a big computer vision conference, and a bunch of the papers just got released. So there's a big flood of computer vision papers that came out in the past week, basically. And I was going through them and I was finding different papers, a bunch of different cool stuff, and I found this one, which was very interesting for a couple different reasons. So one of the first reasons is that it's Adobe Research. So Adobe Research has pretty good research, so you can see the markup quality there. But then this kind of caught my attention here. So they have equal contribution and equal advisory. So you see how the two people here who contributed, the first two authors, who are usually the people who did the work, they're from Zhejiang University and University of California, San Diego, and equal contribution. I'm like, okay, all right, it's a little weird. Like, why do they feel the need to say that? And then equal advisory as well for two different institutions. So you have University of California again, and then Adobe Research, and then also this Kingstar Technology. So it seems like all these different institutions here, these two universities and these two companies, are kind of vying for control of this kind of paper. So when you see the institutions that are associated with the paper kind of like competing to be the one that owns this paper, quote unquote, right? Like the advisory and the contributor kind of credentials, I think it means that the tech is good. So I was like, okay, so it seems like maybe what they discovered in this paper is actually pretty good. And then when I kept scrolling through and I found these, and I was looking at the images or the results here, this looks absolutely crazy. So here you see the standard Lego, I don't know what type of truck this is, but it's like a construction vehicle, and it's kind of a benchmark for 3D rendering. So there's basically, you see these four objects over and over again in 3D rendering papers. So obviously the Lego truck, this ficus tree, the hot dog, and so on. And I've never seen one that is this clean, right? So this is the paper down here, right? The three bottom ones are the paper, and then ablated, so minus and a couple different things probably. But look how much cleaner they are compared to a Nerf. Nerf factor is a little bit of an older Nerf, so it's not like a necessarily representative of the best Nerf that is available now, but this was absolutely insane to me. Like every single one of the little bumps on this Lego truck is very clearly defined, right? Almost to the point that it's better than the ground truth. Like that's something I noticed too. Like look at the ground truth versus this method. It almost looks like the method here is better than the ground truth, which is absolutely insane. So I don't know, it definitely piqued my interest. The fact that you have kind of competitiveness happening on the kind of credentials. You have strong institutions such as Adobe Research, and then you have very impressive results. So that triple combination made it interesting for me. And yeah, we're going to go see what this is about and see if it actually is the truth or whether it's just more hype. All right, let's get to it. So we have 24th of April 2023, so this is 3 days old. We propose TensoIR, a novel inverse rendering approach based on tensor factorization and neural fields. So a neural field is the same idea behind a NERF, right? A NERF is a neural radiance field, and it's basically you have a neural net which can tell you what the radiance, what the color, what the opacity of any point within a 3D volume is, right? And that's when you have an equation that describes some vector that lives in a 3D space, that's a field, right? So you can have a gravitational field is the gravity vector at any instantaneous point in a 3D space, right? Okay, so unlike previous works that use purely MLP-based neural fields, so what they're referring to here is that in most NERFs, the very last part of the neural radiance field model is actually just a little multi-layer perceptron. So maybe they do something a little bit more tricky here. Thus suffering from low capacity and high computation cost. The low capacity refers to the fact that you're limited by the capacity of that little multi-layer perceptron at the very end. And then high computational cost refers to the fact that for every single point inside your bounded 3D volume, you have to perform inference on this MLP. So NERFs are very slow right now because of that. We extend TensoRF, a state-of-the-art approach for radiance field modeling to estimate scene geometry, surface reflectance, and environment illumination. So these are probably going to be the three things that the NERF outputs, or that the NERF model is trying to predict. Our approach jointly achieves radiance field reconstruction and physically based model estimation, leading to photorealistic novel view synthesis and relighting results. Benefiting from the efficiency and extensibility of the TensoRF-based representation, our method can accurately model secondary shading effects, right? Like shadows and indirect lighting, which is kind of what they were showing off here, right? Where you can see how they change the lighting, they change the material. So here they're making it a material that has a little bit more roughness, more specularity. These are properties of basically the textures on these 3D meshes, and you can see how it captures that very well, right? Look at the lighting and then the retexturing of that. And generally support input images captured under single or multiple unknown lighting conditions. The low-rank tensor representation allows us, this is Laura's right here, allows us to not only achieve fast and compact reconstruction, but also better exploit shared information under an arbitrary number of lighting conditions. We demonstrate the superiority of our method to baseline methods qualitatively and quantitatively. Yeah, so just looking at these pictures, it looks like it is an improvement, but we'll have to see exactly how they measure the improvement. Inverse rendering is a long-standing problem, aiming to reconstruct physical attributes of a 3D scene from captured images. Yeah, so right now, the way you do NERFs is you have to capture a bunch of images, usually with a cell phone camera, of some kind of object or some kind of scene, and then you run this optimization process where you're training a neural radiance field, right? You're pushing gradients into this little multi-layer perceptron that starts to capture the scene and the way that it looks from all these different angles. And thus, in that way, what a NERF is really doing is it's implicitly putting the information, the semantic information of a scene into a neural net. And then once you have that, then you can basically do novel view synthesis in that you can basically say, okay, well, what would the scene look like from this camera angle? This problem is inherently challenging and ill-posed, especially when the input images are captured in the wild under unknown illumination. Yeah, so this is a problem too that you see all the time in NERFs, where basically a lot of NERFs are sensitive to the illumination. So if you're capturing a NERF of an object, generally, if you want the best result, you want to have the same lighting at all for every single picture that you're taking. You don't want to take a couple pictures of it and then change the lighting and take a couple pictures from different angles. It won't work as well. So being a little bit more robust to the changing in lighting would be pretty big for nerfs. So it seems like they're potentially suggesting that they have a solution to that. Recent works, learning neural field representations in the form of multi-layer perceptrons. However, pure MLP-based methods usually suffer from low capacity and high computational cost. Right. In this work, we propose a novel inverse rendering framework that is efficient and accurate. Instead of purely using multi-layer perceptrons, we build upon the recent TensorRF, or Tensor, how do you even pronounce this? TensorRF? TensorF? That's probably it. NERF, and then TensorF. Yeah, okay. I think I just discovered what the pronunciation of that is. Which achieves fast, compact, and state-of-the-art quality. Why does it sound like I'm in like a fishbowl? Fast, compact, and state-of-the-art quality. I have like the audio playing back and it just sounds terrible. Let's put a noise gate on this as well. All right. All right, how about now? Hopefully this is better. Is this better? Yeah, maybe this is better. Way better, okay. Which achieves fast, compact, and state-of-the-art quality on radiance field reconstruction for novel view synthesis. Our tensor refactorization-based inverse rendering framework can simultaneously estimate scene geometry, materials, and illumination. So this is going to be what the neural network that they train is outputting, right? NERFs normally output a color and an opacity. This one seems like it has a couple more pieces of information. Benefiting from the efficiency and extensibility of TensorF, our method can accurately model secondary shading effects. Okay, they're kind of just repeating what they're saying in the abstract here. Our approach models the scene as a neural voxel feature grid. Okay, so voxel here refers to a bounded volume of space, right? So this is what a voxel looks like. This is more what when someone says voxel, this is kind of what you should be envisioning, right? It's basically a bounded 3D space where everything is broken up into these little squares. And here the feature refers to the fact that every single one of those little squares inside that voxel is going to have an associated feature vector, right? Where the feature vector is like something that comes out of a neural net. Factorized as multiple low-rank tensor components. Okay, so we're starting to paint the picture here. It seems like maybe each dimension of the voxel will be a different kind of low-rank version of the output or something like that. I'm not sure. Let's keep reading. They'll for sure describe this more detail. We apply multiple small MLPs on the same feature grid and regress volume density, view-dependent color, normal, and material properties. Regress here means that they're using regression at the end of their little multi-layer perceptron. This allows us to simultaneously achieve both radiance field rendering using density and view-dependent color, and physically based rendering using density, normal, and material properties. Okay, so radiance field rendering using density and view-dependent color. What this means is that normally whenever you have a NERF, the way that you actually render it is what's called ray marching, which is a form of rendering where you kind of project rays out from the desired view, right? So it's view-dependent color, and then you
basically add up together all the colors that are along this ray, and then that gives you the final color of the pixel. Physically based rendering is what actually you're doing when you're playing video games. So if you're playing a video game, usually it's not doing ray marching. What it's doing is physically based rendering, where it's actually using lights. It has a light source, and it projects a bunch of vectors outside of that light source, and they bounce off of the mesh, right? And the mesh has some normal. And the reason you need the normal is so that you can say, okay, well, the normal of this object is like this, and the vector that's coming from the light source is like this. So because I have both of those vectors, I can tell you exactly how the light is going to bounce off this object. So that's physically based rendering, right? Ray tracing in your NVIDIA graphics card, what that's doing is it's basically calculating the way that light bounces off your object. It's tracing the rays, right? And if you want to do physically based rendering, you're going to need not just the density and the color, but you're going to need the normal, and then you're also going to need the material properties, right? How specular is it? How rough is it? How shiny is it? Basically, how metallic, how not metallic. We supervise both renderings with the captured images to jointly reconstruct all scene components. We reconstruct a scene using both radiance field and physically based method. Okay, so this is kind of interesting. What I'm starting to read into here is that they're basically using both approaches. So much like you would have two different losses, right? You might have your main loss, and then you might have a regularization loss, and then you run your training process, and you're kind of using gradients that are coming from a combination of your different losses. Here, it seems like they're going to be optimizing for both a kind of a nerf-based loss, and then they're going to be optimizing for this physically based loss, right? So that's kind of what I'm predicting here. Inverse rendering is our focus and primarily enabled by the physically based model. Modeling the radiance field is crucial for the success of the reconstruction, significantly refacilitating. The radiance field is pre-computed and fixed in the subsequent inverse rendering stages. In contrast, our radiance field is jointly reconstructed and also benefits the physically based rendering model estimation during optimization, leading to much higher quality. Yeah, so it seems like by having both of those types of rendering methods pushing gradients into your nerf, into your little model, that you're going to get a much higher quality rendering. And then you'll actually, because you have both of them, you should be able to basically use either form of rendering. Either the ray marching kind of neural radiance field kind of rendering that you see in nerf papers, or the physically based rendering that you would see kind of in more real world video game production use cases. Besides, our radiance field rendering can also be directly used to provide accurate indirect illumination for the physically based rendering, further benefiting the inverse rendering process. Okay. Accounting for indirect illumination and shadowing is a critical challenge. This is especially challenging for volume rendering since it requires sampling a lot of secondary rays and computing the integrals along the rays by performing ray marching. Yeah, so this is the type of rendering that most nerfs do, and it's very computationally heavy because for every single pixel in the image, you basically have to project this ray and then march along that ray, right? The marching there refers to the fact that you're moving along the ray that comes out of the camera, right? And every single step that you take along that ray, you're performing inference on this MLP, on this multi-layer perceptron. So if you have a 128 by 128 pixel image, it's already a huge amount of inference steps, but imagine if you have like a 4K image. It would just be, it would literally take you hours to render that in a nerf. Previous nerf-based methods and SDF, this is a signed distance function. It's basically another way of representing a mesh. Either simply ignore secondary effects or avoid online computation by approximating these effects in extra distilled MLPs. So approximating these effects in extra distilled MLPs. So what this means is that you can take the MLP that represents your nerf, and then you can distill it into a smaller MLP that is potentially small enough where it makes your computation a little bit faster, right? So that's these two papers here. It seems probably do something like that. In contrast, owing to our efficient tensor factorized representation, we are able to explicitly compute the ray integrals online for accurate visibility and indirect lighting with the radiance field rendering using low-cost second bounce ray marching. Okay, so I haven't heard about second bounce ray marching, but probably refers to the first bounce is when it first comes out of the camera, and then when it hits the mesh, and then you have a second bounce. So that's probably what's referring to. It's the second bounce, the first time it bounces off an object. But in order to calculate that second bounce, you're going to need to know what the normal vector to that object is, which most NeRFs do not give you that kind of normal vector. In addition, the flexibility and efficiency of our tensor allows us to perform inverse rendering from multiple unknown lighting conditions with limited GPU memory. Multi-light capture is known to... This isn't necessarily... we don't know what that means, right? Like, we don't know what limited GPU memory means. It could still be prohibitively expensive and impossible for someone to do in their house on their GPU. Multi-light capture is known to be beneficial for inverse rendering by providing useful photometric cues and reducing ambiguities in material estimation. Since each lighting condition corresponds to a separate radiance field. Yeah, so this is an issue, is that sometimes in NeRFs, like, not only is a single scene a different NeRF, so if you have one picture, if you have like this, you would have a NeRF that just represents only this object, you would have a NeRF that represents only this armadillo, you would have a separate NeRF that represents only this hot dog, and for each one of those you have to train it from scratch, which is really annoying. What they're saying is that with NeRFs, not only is that the case, but then you also have to have a separate NeRF if you wanted to do a different type of lighting, right? If so, you had the same object, but with different lighting, you would need a different NeRF, because all the NeRF is storing is the opacity and the color. There are techniques that can relight NeRFs. I've seen that before, but I think they're still pretty slow. We propose to reconstruct radiance field under multi-light in a joint manner as factorized tensor. Extending from the original TensorIR representation that is a 4D tensor, we add an additional dimension corresponding to different lighting conditions, yielding a 5D tensor. Okay, there you go. They're basically going to expand the dimensionality of the feature that comes out of this tensor such that you can have a kind of a lighting dimension. To explain the variations, we store this 5D tensor by a small number of bases whose outer product reconstructs the 5D tensor. So this is the factorization part, right? Where it's basically they're taking that tensor and they're decomposing it into smaller, what they're calling here bases. But then basically you can multiply those together and get the original tensor. So it's kind of like a factorization, like a decomposition of the higher dimensional tensor into these like little parts. When multi-light capture is available, our framework can effectively utilize the additional photometric cues in the data, leading to a better reconstruction quality than a single light setting. A little bit. Our approach can reconstruct high-fidelity geometry and reflectance of a complex real scene captured under unknown natural illumination, enabling photorealistic rendering under novel lighting conditions. We evaluate our framework extensively on both synthetic and real data. Our approach outperforms previous inverse rendering methods by a large margin qualitatively. Yeah, this is what I noticed. Very, very impressive. Achieving state-of-the-art quality in scene reconstruction for both geometry and material properties. Owing to our efficient tensorial representation and joint reconstruction, our approach also leads to a much faster reconstruction speed than previous NeRF-based reconstruction methods while achieving superior quality. And here's the little summary of all the different things they did in this paper, which you can usually find at the end of the introduction. So if you're trying to be super fast about going through these papers, and there's a lot of papers right now, so generally look at the picture, read the abstract, and then scroll to the end of the introduction and see if they have one of these sections, and they'll straight up just tell you everything that they did. So here are the three things. novel tensor factorization inverse rendering approach, right? So it's basically a slightly new kind of NERF based around tensor factorization, leading to state-of-the-art scene reconstruction, an efficient online visibility and indirect lighting computation technique. Okay, so this is going to be the relighting, so the ability to change the lighting on this NERF. It's not a NERF, I should call it the TensorF, right? And we enable efficient multi-light reconstruction by modeling an additional lighting dimension in the factorized tensorial representation. So kind of adding a dimension in the kind of, I don't know if latent space is the right word, but kind of in the manifold that this MLP predicts, such that you can kind of move along that new dimension and change the lighting. All right. Related works. So here they're going to reference all the different NERF papers. So neural representations, there you go. They reference here 6 different NERF papers. Are a promising alternative to traditional representations like meshes, volumes, and point clouds. So meshes are what you see in video games, right? You have a mesh with a texture, there's triangles, there's vertices. Point clouds are what you would have in an autonomous vehicle or in a robotics use case where you have a LiDAR that gives you depth for every single point, and then you have a color for every single point. Compared to traditional representations, neural representations are more flexible and can accurately reproduce the geometry and appearance of real-world scenes. Yes, NERFs are very good and they're very popular, and there's a reason that they've kind of been growing like wildfires, because they kind of represent a new fundamental way of doing 3D rendering. And I feel like my prediction is that all of the forms of 3D rendering that we have now, all the way that video games are done, the way that computer vision is done, or not computer vision, the way that CGI is done for movies, like all of that is going to be replaced by NERFs. And the only thing that's standing in between that is like kind of preventing that is the fact that NERFs are still a little bit too slow, a little bit too long to train, a little bit too annoying. You need to have pictures of everything. So there's a couple things that are preventing NERFs from kind of taking over, but I feel like it's inevitable and they will take over. Have been proposed. Originally, neural fields are modeled in the form of MLPs, which have limited capacity and high computational cost. But many works recently introduced more efficient representations that combine neural feature maps and volumes and accelerate the training and rendering. And this work is based on the TensorF, tensor factorized neural representation. Inverse rendering. Okay, so this is, I want to kind of read this, but let's finish the related works and then we'll get into that image. Abundant works have been able to infer the geometry and material properties of real-world objects from image collections. They typically represent the scene geometry using triangle meshes, so this is the mesh and texture technique, or can be pre-constructed with a depth sensor or multi-view stereo techniques. So this is how you can get depth without, in a synthetic scene, right? If you have a synthetic objects such as these armadillos and these things, these are actually meshes, so you can get a ground truth normal vector, you can get a ground truth position, you can get a ground truth vertex position. But if you're using a real world scene, you don't have the ability to get ground truth depth. So that's where depth sensors and multi-view stereo can give you an approximation of that. To make use of learned domain, in this work we jointly estimate the geometry, materials, and lighting from images captured under unknown lighting conditions with neural field representation that is more efficient and robust. They are limited by usage of computation-intensive MLPs. And here, the computation-intensive, it's not that MLPs are computationally intensive, right? MLPs are actually the simplest neural networks that you can have, right? It's just a multi-layer perceptron, just a couple layers of fully connected neurons. The part that makes it computationally intensive is that you have to basically evaluate it for every single ray that you're casting into the scene. This inefficiency adds extra burden on inverse rendering when computing secondary shading effects, which requires extensive sampling of secondary rays. In contrast, we base our model on the advanced tensor representation utilizing factorized tensors to achieve fast reconstruction. Our tensor-based approach supports fast density and radiance evaluation, enabling efficient online computation for secondary effects. Our model is easily extended to support multi-light capture by modeling an additional lighting dimension. Okay. So let's look at this. This is the big picture that shows you their entire pipeline here. So we're not going to understand anything because we still haven't even read the actual method paper here, but I think that should be able to kind of like get a sense of all the different parts here. So you have here a voxel, right? You have a voxel of space. Inside of it is a hot dog. We see a camera with a certain origin and a ray that is being projected through the voxel with a view direction D, right? Along each point in that ray, you're sampling from a multi-layer perceptron that represents that scene. That is your nerve, right? xj equals O plus tjd. I guess all this is really saying here is the point at J is equal to the origin plus however much whatever distance you're going along that ray times the distance D there. So that just seems like a pretty standard way to get the exact point. Tensor factorization based scene representation. So you have a density tensor and an appearance tensor, right? So maybe these are two different things that you're trying to learn, right? Appearance is going to be your radiance, your material, and your normal. So this radiance is going to be radiance, material, normal. These are all properties of basically the texture in physically based rendering with a mesh and a texture. Normally these are all properties of the texture, right? Or of the texture or the surface of the object, right? You have the normal vector, you have the material itself, which is probably predicting the specularity, the roughness, things like that, and the radiance, which might be the color. And then the density is just what in most NERF papers it's called the opacity, and it's basically just how see-through is this object, right? And I think the density and the opacity is like, that's actually usually what leads to NERFs having this like almost like a cloud effect, right? Like in most NERFs, like there's this kind of like diffuse cloud effect that happens where it looks like it's like misty, right? It's like not, the objects aren't fully formed. They just kind of like start appearing out of nowhere. You don't get really hard edges, right? And in this paper, they do get really, really hard edges. Those edges are very crispy, right? So curious what kind of regularization or how they actually achieve that. Okay, so here we have 3 different networks for each of the different appearance properties here that it's trying to predict, but I don't see a network here for the density, which is a little bit weird, right? That's telling me that they don't actually have a neural net that tries to learn the density. We'll see exactly what happens there. Okay, but then you have 2 different rendering processes here. You have the radiance field rendering, which is the ray marching, which is basically what most NERFs do. And most NERFs would basically just take the loss from this right here, this rendering, and then feed that back into their models. But here, it seems like not only are they feeding back the loss from this radiance field rendering, right, this ray marching, but they're also feeding back the loss here from physically based rendering. So they've formulated some kind of loss for physically based rendering that they can feed back, right? This LD, right? We don't really know what CRF is and CGT. I think this probably refers to the color. So the color of the radiance field, which is what's coming out of here. And then the CGT would be the ground truth color. And then here the double parallel bars just means that it's the absolute value. And then the 2 here means that it's an L2 loss. So L2 loss means that they square the error. So things that are very close together are going to be much quadratically less big. It's a really confusing way to say it, but basically if you square your error, right, the difference between an L1 and an L2 loss is that the L2 loss, the squared, penalizes differences that are very big, right? Here down here you have a similar kind of loss. You have CPB, so I guess this is the color for physically based rendering, and then the that's also using the color from the ground truth. So the difference between those, also L2 loss. We don't know what LD is. It's coming from an environment map here, so I don't know. We'll see what exactly this is. But you have here one loss, here a second loss, here a third loss, LD, and then there seems to be a loss here as well, LIND. So there's some kind of loss between the radiance field rendering and the physically based rendering, and then I don't know what V is. It will probably tell us what V is. So, okay, so basically, like, looking at this, it seems like what they're really doing is, and what's novel about this paper is that they're combining physically based rendering and radiance field rendering in such a way that you can get losses from both of those, feed it back into your multi-layer perceptrons that parameterize the NeRF, or in this case, the TensorIRF, and then from that, because you have two different kind of loss functions that are pushing gradients, the final models here are not just getting good at estimating the color, but they're also getting good. They're also starting to learn an implicit understanding of like the actual material and object in the scene itself. So I think this is a simple concept, and I like it. Let's see. Multiple MLPs to regress volume density. So here we go. We got volume density, view dependent color C, the normals N, and material properties, BRDF parameters. So if you guys have ever used like any kind of 3D program such as Blender or Maya or any of these, generally you have editors for the material properties of textures, and BRDF is pretty standard thing there. So those are the material properties. Beta, that's this, right? The material net predicts that material properties, enabling both radiance field rendering and physically based rendering. In particular, we march a camera ray from a camera origin O in viewing direction D, sampling points xj along the ray, and applying radiance field rendering using the density and view dependent colors regressed from our representation. Right, so they've basically defined all these different terms here. We also use our volume rendering weights to determine the surface point x hat. So there's some point on the surface, x hat, right here. So you see this x hat that refers to the point on the surface. D is the view direction, and then WI, I guess, is the incoming light direction. I wonder how they get that, because you're not going to have access to the incoming light direction unless you're using a synthetic scene. So see, potentially a flaw there. Visibility V and indirect lighting LIND. Okay, so now we know what LIND means. LIND here is indirect lighting. Using radiance field rendering, we supervise both the radiance field rendering CRF and physically based rendering CPB with the captured images in a per scene optimization for joint scene reconstruction. And the joint here refers to the fact that there's two different kind of losses and two different paths which are being used to produce gradients to train these models here. Okay. Reconstruct scene geometry, materials, and illumination from multi-view input images under unknown lighting. Unknown lighting, so they don't have any explicit knowledge of the lighting, which kind of conflicts with this, right? Like, where are they getting the indirect lighting and the incoming light direction if they say they're using unknown lighting? Let's see. We leverage rendering with both neural radiance fields, physically based light transport. We introduce a novel TensorIRF-based scene representation that allows for both rendering methods. Also supports capturing under multiple unknown lighting conditions. We simultaneously estimate all scene components in a joint optimization framework. We apply ray marching to achieve differentiable radiance field rendering as done in NeRF. So this is this part here. Actually, you know what I'm going to do? I'm going to open this paper in a new thing just so we can have that figure there where it's convenient, right? Because I'm going to keep having to scroll up and down just to get to this figure. So let's do this. So we have this figure available, and then we can, yeah, right? So I can scroll down here and we can edit it. We apply ray marching to achieve differentiable. So there's your ray marching right here, right? You have your ray, you're marching along your ray. We further determine the expected surface intersection point for each ray using the volume density. Okay, so if you have the density vector here, the opacity is another way to call it, then you can say here is where the density is the highest, which probably means that's where the surface of the object is, right? So there's a little bit of a bias there where they're using a, not a bias, but a prior, right? They're prior, as in like one of the assumptions that they're using. You could have a Gaussian prior, or you can have a prior that's more just like a high-level concept. And here, one of the priors that they're using is that, hey, at the very peak of the opacity curve along the ray, we're going to assume that that probably represents the surface of the object. Given a camera ray RT, so here's the actual ray. So you have an origin and you have a direction. And then you have endpoints along the ray. Right, so this is just basic nerf math here. Right, so for all your endpoints, you're summing over every single one of your endpoints here. Right, along the ray. Each point has a density. It has a step size. It has a view-dependent radiance and a volume transmittance. Used in this way here, right? You have 1 minus the exponential of the negative of the volume density times the step size, right? You multiply that all by the color and then the transmittance. And then you add up all of those and you should get one final color, right? And here the transmittance is just exponent of negative sum from q equals 1 to j minus 1. So this is all the points up until that point, right? So here, for each, as you're summing along the ray, right, you get to point j, and then this transmittance here is only a function of all the points up until that j. So the j, the transmittance here, doesn't account for the stuff after the point in which you're calculating. Physically based rendering. Okay, so that's the nerf-based rendering, which is this, but now we also have physically based rendering, which is this part down here, right? This is the physically based rendering. We apply a physically based parametric BRDF model. This is kind of exactly what you would have in something like Blender. Use the green there. And perform physically based rendering using predicted geometry and material properties at surface points along the camera rays. These surface points x hat, and we don't know exactly how they're getting it, but naturally determined using the volume rendering rates and weights and sampled from equation 1. So they're getting the surface points from the radiance field. A little kind of like a chicken and an egg problem, right? Like, how do you get the original surface points? Okay, so here, x hat, which is the surface points, is equal to the summation from j equals 1 to n, where n is the number of points that you're sampling along the ray, right? So n is here. N in this case would be 1, 2, 3, 4, 5. So n is 5 in this image, but I bet you it's a little bit more than that. It's probably something like 10. And this is the integral over this omega here. What does the omega mean? It means upper hemisphere. Wait up, I skipped an equation here. Okay. Are naturally determined. Okay, so x hat, which is the surface, summation over all the endpoints in the ray of wj, where wj is what? Wj is, did they define that? Oh, wi is the direction of the lighting. So I still don't know how they're getting that. I don't know how they're getting the direction of the lighting. Like, it seems like they're just kind of getting that from, okay, no, wait, here it is. WJ. Oh, no, wait up. These are separate W's. This, you see this? This is a W, but this here is a lowercase omega. Lowercase omega. Let me make sure my Greek letters are correct. Yeah, so capital omega looks like a horseshoe. Lowercase omega looks like a little script W. So there's actually a difference here. You see, this is WJ with a little script, and this is this is omega. So these are slightly different. That's a little confusing, but luckily we caught that. So here, this isn't referring to the light direction. This is referring to this weight, right? And this weight is basically the same thing that we had here. It's basically just the transmittance and a function of the transmittance and the density and the step size. So basically how far along you are, how much of the total density, kind of almost like a way of normalizing the density along the ray. We leverage the classic surface rendering equation to compute a physically based shading color with an integral over the upper hemisphere at each surface point. So what do they mean here by integral over the upper hemisphere at each surface point? Is that when you're calculating ray marching based rendering, right, you're basically just going down this ray and you're adding together every single sample, right? So you're saying, okay, here I have a partially see-through point that is brown, and then I have the next thing I have a partially see-through point that is blue, and then I basically just add them all together here, right? So it's adding blue to gray to blue to gray, and then you add them all together, you get the final color. Whenever you're doing physically based rendering, you're actually calculating all the light bounces, right? So you have some surface point, and then you have a normal vector, and that normal vector defines basically a hemisphere over that point, right? So if you know the normal vector is like this, you can basically draw a little hemisphere around that normal vector and say, I'm going to integrate over that entire normal vector, or that entire hemisphere. And that's what this integral is doing here, right? It's an integral over the entire hemisphere, or basically kind of the normal direction of the surface point, right? So here, integral over capital omega, which is the upper hemisphere, and then d omega I, right? Where this is all the different lighting, all the different vectors of lighting direction. What do you have here? Li is a function of x hat and omega I, so this is the incident illumination. Right color here. We have incident illumination, which is a function of the surface point, and then omega I, which is basically a vector, which is illumination direction. You have FR, which is the actual physically based rendering, and this is a function of the surface point, the direction of the light, the D, which is the view direction, and then beta, which is, what is beta? What did they tell us with beta? Beta and N represent spatially varying material parameters, so albedo and roughness. These are two standard parameters in a BRDF material property, right? So that's good. Sorry, I was almost scrolling up to the thing that rather than actually at it. So here we go. The beta is going to come out of your material net, and N represents the roughness, which is coming out of your normal net. I don't know why this is probably wrong. N probably represents the normal vector. Oh, yeah, okay. So beta represents albedo and roughness, and then N represents the surface normal. Okay, that makes more sense. I was like, why is N the roughness? That doesn't make any sense. So here we go. So beta and N. Beta is the roughness and albedo, and then N is the normal vector. And there's two separate networks here to calculate that. The roughness comes from the material network, and then the normal network just gives you the vector. In theory, accurately evaluating this integral in equation 3 requires extensively sampling the lighting direction and computing the incident lighting to account for shadowing and indirect illumination. Yeah, and when you're doing when you see like a video game that advertises like ray tracing, right? What what do you get from that? So what you get from that when you have a ray tracing video game is that you have very good shadows, right? Like the shadows of your character are like basically they're real, right? Like you can the exact shade of your like let's see. Ray traced lighting. Right, like things like this. Like for example, you can see the shadow of this tree is like accounting for the fact that there's like all these little branches. So look at how nice those ray trace shadows are. And in order to do that, it actually it's very, very expensive because you have to calculate every single one of those lighting rays, right? You're basically taking every single light source and all these rays are coming out of that light source, and you're basically calculating, okay, this ray coming out of this light source here is going to bounce off of this object here with this normal, and then it's going to bounce off of this object here with this normal, and then it's going to bounce off of this object here with this normal. And usually you only calculate up to a certain amount of bounces, so maybe 2 bounces, 3 bounces, 4 bounces. And I think here they actually said that they're going to do 2 bounces. Right, so camera ray computation, and then they're going to have second ray computations. So they're going to have 1 bounce of light. And these are extremely computationally expensive, yes. Ray-based rendering is very hardcore in terms of computation. Previous nerf-based methods often simplify it by only considering direct illumination, or using extra auxiliary multilayer perceptrons to make approximations and avoid full ray marching. Instead, we evaluate the integral more accurately by marching secondary rays online and computing the incident lighting. Oh shit, this is pretty cool. So they're using ray marching on the secondary rays. That's fucking crazy. So normally when you have a nerf, right, you have one ray, which is coming from your camera. They're going to call this the camera ray. That's the first ray. That's the one that you're actually cutting up into little samples and then evaluating your nerf at. But the way that they said this here, marching the secondary rays, it seems like they're going to do the same thing, but for the bounce that comes out. So you have your green ray here that is coming from the camera, and then you have the bounce of the lighting, and then it seems like they're going to do that there as well. That's pretty cool. I don't know if I've seen that before. This is made possible by our novel efficient TensorRF-based scene representation. So let's hear about this magical tensor-based representation. We now introduce our tensor factorization-based scene representation that simultaneously models volume density, view-dependent color, shading normal, and material properties. Our method can model the scene under both single or multiple lighting conditions. So what they're referring to here is whether there's one light source or multiple light sources. We first introduce the single light setting in this section, and we'll discuss the multi-light extension in section 3.4. At a high level, radiance, geometry, and material properties can all be represented as a 3D field. Radiance, geometry, and material yeah. So radiance, geometry, and material properties can be represented as a 3D field if you assume that the field or that the scene is static. And that's something that they haven't mentioned at all, but this is an entirely static scene, right? There's nothing moving. Everything is still. And that's a limitation of nerfs too, is that there are nerfs that use time as well, but nerfs that have time are still very much a research problem. I haven't seen someone solve that issue where it's like, hey, can we actually have a nerf video that's actually like really good? Usually the nerf videos are very small, very short duration, low frame rate. And this paper is no different, right? It's basically a static scene. We can use a feature volume and a voxel feature decoding functions to extract information at any point of the 3D field. To compress the space of the feature volume and also regularize the learning process, TensorF proposes to use a low-ranked factorized tensor as the feature volume. So specifically, the one that they're going to use is the vector matrix factorization proposed by TensorF. So this is the factorization. It's basically a way to take a high-dimensional tensor and then break it into these like factors or components, right? In particular, we use, let's actually see if ChatGPT can give us a better definition. I feel like I'm not, guys, just, can you explain tensor factorization like I am in high school? How about that? I was going to say like I am 5 years old, but then I feel like the 5-year-old explanations are not as good as the high school. Tensor is a multi-dimensional array of tensors. Okay, cool. Scalar, vector. Okay. Wow, it's really slow this morning. What's going on? Matrix, blah, blah, okay. Come on. Factorization is the process of breaking down a complex object into simpler parts that can be multiplied together to reconstruct the original object. It's like taking a large number and breaking it down into its prime factors. Tensor factorization is the goal of tensor factorization is to break down a high-dimensional tensor into a set of lower-dimensional tensors that, when multiplied together in a specific way, can approximate the original tensor. And here it has a little analogy for us based on a Rubik's Cube. That didn't really help us, but basically there's a specific type of tensor factorization that they're going to use. We use 2 separate VM factorized tensors. Okay, so there's actually a feature grid specifically for the volume density, and then there's a feature grid specifically for the appearance. So they're separating that out. They don't have one feature grid for everything, right? So here, the same way that they split out and they have different networks here for the different things, or for each of these different properties, where they have the albedo, roughness, they have the color, they have the normal, they have a separate network for that, right? You could see how they could use one network that predicts all of these things, but they chose instead to have 3 networks that each predict a separate thing. And they're doing a similar kind of separation here, where they're going to have separate feature grids for the volume density and the appearance. So, and this is capital G here. For script G, I don't know exactly what that is. Is that script capital G LaTeX? Yeah, script capital G. Wanted to make sure that wasn't a Greek letter. The appearance tensor is followed by multiple lightweight MLP decoders to digress various appearance properties. Okay, so that's actually here. That's what this alpha is here, or this A. Okay, this makes a lot of sense. So here, the 5D tensor that they're referring to is actually this part here. So they have a separate density tensor, a separate appearance tensor, and then the appearance tensor is actually what gets fed into the radiance net, into the material net, into the normal net, and then gets used to produce the individual color, roughness, and normal for an individual point in the 3D volume. So that's kind of cool. Density tensor. The density tensor is 3D and directly expresses volume density without any network. Specifically, the VM factorized density tensor is expressed by the sum of vector matrix outer products. So this little dot here, this little open circle here, is the outer product of a matrix, right? So you have the outer product of M, Y, Z, which is, it's 3-dimensional, right? So you have X, Y, Y, Z, and then ZX. You have basically the 3 different kind of views of it here. The summation over K, what is K? K is the kth vector and the matrix factor, so you have K different factors. Wonder what K is in practice. And you're summing over all the 3 different things here, right? So here they have the equation written out exhaustively, and then they have the equation kind of like written in a more compressed form by having 2 summations here. represents the kth vector and matrix factors of the corresponding spatial axes M. So M is the spatial axes, right? You have 3 different spatial axes here. For simplicity, M bar, or M tilde, denotes 2 axes orthogonal to M. So each pair of orthogonal axes. So X tilde represents the Y and the Z. And the appearance tensor is going to be 4D. So this is the density tensor. They're saying that one's 3D, and then the appearance tensor here is going to be modeled similarly by a vector matrix of spatial factors and additional feature basis vectors B. What is that? So you see how in the density one, you don't have any additional feature basis vectors. It's literally just the V times the M, the outer product of V and M. But here, you have the same outer product, but you have an additional outer product, which is going to be a feature grid. And this is probably where they're going to do their lighting. I'm guessing this is where they're going to sneak in their 5th dimension, which they were talking about earlier in the paper. We obtain density directly by linearly interpolating the density tensor and applying multiple MLP networks to decode appearance properties from interpolated appearance features. So that they're referring to this process here. So here you can just go, you directly interpolate inside this density tensor space and you get the actual density at any point in space. So that's done without any neural networks, but the properties here are done with a neural network. So there's a neural network that receives potentially all of the appearance tensor, probably just a slice of the appearance tensor or like a specific point within the appearance tensor, and then it calculates the properties from that. To decode from interpolated appearance features. So we don't know if there's some kind of like if it's giving it all of the appearance tensor or if it's just giving it like a little part of it. I assume it's probably just a little part of it. So the 3 networks that they have here are the radiance network, the shading normal network, and the material network. So those are 3 different multi-layer perceptrons, right? You have your 3 different multi-layer perceptrons here called radiance net, material net, and normal net. And here they're calling them radiance net, shading normal net, and material net. And our scene representation is expressed by this. So you have your density tensor, you have your appearance tensor, and then your color, your normal, and your material properties are the result of feeding your appearance tensor through each of the networks, each of these little MLPs here. X denotes an arbitrary 3D location. Right, so the fact that if X denotes a 3D location and you have a tensor which is a function of X, then to me that means that maybe they're just feeding only the specific point inside that tensor. They're not feeding it the whole thing. And our linearly interpolated density and multi-channel appearance features computed by linearly interpolating the spatial vector and matrix factors. Okay, so I guess kind of what they're referring to here is that this density tensor and this appearance tensor, they're not going to be kind of infinite resolution, right? There's going to be, I don't know what these are, maybe 10 by 10 by 10, probably a little bit more. There's probably more there, but it's going to be limited, right? Versus when you calculate when you project a ray from your camera through your voxel and you get the endpoints along that ray, those endpoints are going to be much more precise, right? It's going to be like position 0.001, 0.1, and then 0.0001, right? So like the density tensor doesn't have that level of resolution. So you're going to have to interpolate to figure out what the value of the density tensor is for that exact point that you're sampling along this ray. So that's where the interpolation is coming in, right? Because these appearance and these density tensors are not going to be as high resolution as the voxel in which you're getting your points X from. Volume density and shading normals both express scene geometry and high frequency geometric details. View dependent color and physical shading properties. Duplicatively model the scene appearance, determining the colors. We bind shading normal with volume density using a regularization term correlating the scene geometry estimation reasoning. So I think here they're referring to the fact that maybe these terms here, this V and this Ln, the fact that there's a little bit, you can use regularizations from the radiance field rendering for the physically based rendering, and then you can use regularization from the physically based rendering for the radiance field rendering. I think that's probably what they're referring to there. Which is the benefit of using this kind of joint optimization, is that you can use kind of signal from one part of the joint optimization to kind of help the other part of the joint optimization. In essence, our tensor F-based scene representation provides scene geometry and appearance properties that are required for both radiance field rendering and physically rendering. This joint representation, which I think is the most powerful part of this paper. And it's such a simple concept, so it's kind of weird that like there's novelty in doing that, right? It seems like it's a very simple concept to just say, hey, let's just take a nerf, but then also do physically based rendering at the same time and see what happens. But hey, you know, if it works, it works. We let the two sub-representations share the same neural features in our tensors, allowing their learned processes to benefit each other. While the physically based model is our main focus and achieves inverse rendering, modeling the radiance field can facilitate the volume density reconstruction and also regularize the appearance features to be meaningful since it has a shorter gradient path. Interesting, okay. So they're saying that the gradient path that comes out of the neural radiance field is shorter, right? Shorter there refers to the, when you have a neural net, right, and you have a multi-layer perceptron and there's a bunch of layers, right? Every layer that the gradient has to get through slows it down, right? This is sometimes called the vanishing gradient problem, where if you have a ResNet 50, ResNet's a bad example because of the residual connections, but if you have a network that has 50 layers versus 100 layers, the 100 layer network, it's like those gradients need to go through so many more extra layers that by the time they get to the bottom layer, they're kind of spent, right? They're so tiny that they minimally impact the weights. So of course, there's residual connections and skip connections, right, which are kind of a solution to that, but there still is a difference there. And they're basically saying that the radiance field, not the radiance field, the neural, or not the radiance field rendering provides a shorter path than the appearance tensor. And maybe what they're referring to here is that you see here how the density goes, the density is calculated directly from the density tensor. There's not an additional multi-layer perceptron here that needs to have gradients pass through it. So you take the loss from here and you can go directly into this density tensor versus here for the physically based rendering, you take your loss and you have to go through both of these little MLPs here, the material net and the normal net, before you can get to the appearance tensor. So the gradient path is different for these two different rendering techniques, which I think is why they probably play nicely together. Okay. In addition, the radiance field can naturally provide indirect illumination for physically based rendering, enabling more accurate physical model reconstruction. All right, let's see. We compared normal and albedo reconstruction results between our joint reconstruction model and an ablated model without radiance field rendering during reconstruction. Okay, so no radiance field. This is an ablation study. So what they mean is that basically they remove the radiance field. So they're just going to use only this physically based rendering part of their joint optimization process. And then they're going to see, okay, well, how is this different? If we only use the physically based rendering, how does it change the result? And you can see here, ground truth versus the R's. And honestly, like it literally looks better than the ground truth, which is fucking crazy. Like, look at that. It's like almost crispier than the ground truth. And then you can see without the radiance field, you get all these like weird looking artifacts. Yeah, so the fact that this one looks way better than this one is telling you that the radiance field is very important, right? They performed an ablation study to show you that the radiance field is critical. And if you get rid of it, you're basically going to get bogus results. All right, let's see. Figure 4. We show our computed indirect illumination of the full rendered image and our lighting visibility under two different directional lights. So indirect lighting, and then lighting visibility under two directional lights. So really what you're looking here, directional lights just means like a light that has kind of like a specific, it's coming from a specific kind of point in the voxel, right? You have your little voxel of 3D space, you have your hot dog object sitting there, you have a directional light that's coming straight at it. So because their technique is estimating the normals here, right? They have a pretty good implicit representation of the normals and the material and the surface and the location of that object and everything, right? That all of that is in some way implicitly stored inside the weights of the little MLPs. You can see that it actually is pretty good at that. It knows that if there's a light coming from this direction, that this side of the hot dog is going to be illuminated, but the inside of the hot dog is not going to be illuminated. And that's kind of what they're showing off here, is that the representation of this scene that they've learned from this joint optimization process is good enough to understand how different directional lights would play on this object. That's what they're trying to show you with that figure there. Okay. What is going on here? Jesus. Help me, baby Jeeps. Okay. Illumination and visibility. Our tensor-based scene representation is highly efficient for optimization and evaluation. Especially, our volume density can be computed by simple tensor interpolation without using any MLPs. So what do they mean by this? What they mean by this is that normally, if you have in most NERF papers, the density here, this little sigma here, is calculated from a neural net, right? So there's a neural net that you give it a point in 3D space, and it'll say, oh, here's the density for that point. And you're like, okay, well then what's the density here? And it's like, okay, here's the density for that point. And what's the density here? Here's the density for that point, right? So basically you have to explicitly calculate the density at every single point in 3D space in order to get a estimate of the volume or the volume density, right? But in this paper, because they use this tensor, right? They basically have this tensor that over time learns the density of that scene. You can just take this density tensor and get the density directly from that in one shot, right? Like basically it gives you the density at every single point in space. You don't need to be doing this kind of constant or doing inference with an MLP like a million times in order to get the density. You can just directly get the density from this density tensor. That's another huge advantage of using that tensor representation. Leading to highly efficient computation of volume transmittance and rendering weights. Highly efficient. This allows us to compute accurate incident illumination, LI. Highlight that little term there. That accounts for secondary shading effects with ray marching as shown in figure 4. In particular, the incident illumination is computed by this. So incident illumination, Li, is a function of x hat. X hat is the surface point, which they determine by looking at the peak, or just looking at this density tensor, actually, to be honest. And omega I, where omega I is the lighting direction, right? And then this incident illumination, which is a function of the surface point and the lighting direction, is composed of two different parts here. You have LD, which is the direct illumination, which is just a function of the lighting direction here, omega I. V, which is the light visibility function. I don't really know what the fuck that means, but I think it's the V here. What is the light visibility function? It's probably maybe some kind of mask or something like that, that like once you get to a certain peak in the density, then you don't have light after that or something like that. Maybe it's just like a simple kind of like a step function or something like that. I don't know. The fact that they don't define it means to me that it's maybe a little bit Actually, no, here you go. It's down here. Okay, so we'll define it later. And L-ind is the indirect illumination, and the indirect illumination is just also a function of the x hat, which is the surface point, and omega I, which is the lighting direction. All right, direct illumination. We assume that unknown natural environment to be distant from the captured object and represent the global illumination as an environment map. Parameterized represent the global illumination as an environment map. Okay, so this is what their environment map over here is, right? So in this bottom corner of this image, you see this thing called the environment map. And when you're doing HDRIs, so if you guys haven't heard this term before, an HDRI is a type of background that people use, and it's kind of like a skybox, right? A video game, you have like the whole sky is actually one object, right? It's just one object, and it includes lighting, right? So it tells you what does the environment look like no matter where you look, and then it also gives you lighting. And HDRFs are pretty popular in the 3D world, and I think that's what they're referring to here, is an environment map is kind of like an HDRF. Parameterized by a mixture of spherical Gaussians, which represent the direct illumination. So spherical Gaussians basically just means a Gaussian that's defined on a sphere, and of course you can assume that any environment, right? Any lights in your environment, or your environment can always be broken down into basically a bunch of lights, where you have, assuming that each light is basically a little Gaussian, and you basically have a bunch of together, right? So it's a mixture of these, a sum of these. But there's going to be an assumption there, right? At some point they're going to say, okay, well, how many Gaussians, right? Is it 2 Gaussians, 3 Gaussians, 4 Gaussians, 10 Gaussians? So curious what they probably use for that. In contrast to previous methods that use spherical Gaussians for computing the integral rendering equation, we use spherical Gaussians only for its compact parameterized representation and compute the integral numerically by sampling secondary rays and performing ray marching. Okay, so here's where they're actually going to be doing that. The visibility and indirect illumination. We make use of the jointly trained radiance field to model secondary shading effects. Yeah, this is the crazy part to me. This is like kind of where this paper gets a little crazy, is that so you have this kind of joint optimization process, right, where you're both using physically based rendering and neural based rendering or radiance field rendering to push gradients into the same set of things here, into the density tensor, appearance tensor, and these different little MLPs here. But you can also use the radiance field to calculate the secondary illumination effects here, right? This omega I second ray computation. So this is like a kind of a 500 IQ move here, where they basically use the fact that, hey, well, actually I have a neural representation of this scene. I can just calculate the secondary lighting effects using that neural representation, and then use it to push additional gradients into my physically based rendering pipeline. So this is pretty tricky here. Like whoever came up with that, that's some crazy shit. More specifically, the indirect illumination arriving at the surface point from the indirect illumination vector is inherently explained by the radiance color, CRF, along the ray. Right? The visibility function is exactly modeled by the transmittance function in volume rendering. Okay, so in your volume rendering, right, you have this transmittance term, which was up here. Where is it? Here it is. The transmittance term. Transmittance is calculated at every single point in the voxel, right? And you can calculate it, and it's just a function of the density at that point, and then how far along in the ray you are, right? The step distance, what they call it here, step size, right? So how far along you are in the ray, right? And then the opacity at that point. And they're saying that actually those things are exactly what you need to calculate the visibility function. And the visibility function is just literally going to be that. So here you go. The visibility function, which they use here to determine the incident illumination, is a function of the surface point and the indirect lighting. And that itself means that because V is a function of that, then you can just, and t is a function of the color of the radiance field, you can say that the indirect lighting is a function of the color of the radiance field. So this right here. This is the magic that they did here, where they realized that the color of the radiance field, right, this part right here, CRF, the part that comes out of your radiance field rendering, can be used to calculate the secondary ray computation and get an extra gradient, an extra regularization term there. For such an insightful set. Yeah, hopefully it's useful. You know, feel free to interrupt with questions. You know, I feel like sometimes these papers are a little bit math heavy, a little bit concept heavy. They can be a little confusing, and yeah, I don't want to make it seem like I'm like a, you know, PhD like math professor here. You know, like I'm also just some guy who's sitting here figuring it all out. You know, and there's still plenty of things that I don't really fully understand. So any part that you're like, hey, how does that work? Just feel free to interrupt, and we can spend some time kind of learning it together. Yeah, I don't want to like alienate my community. You know, I want to make sure that everybody feels like they're learning something, and they don't feel like this is too advanced. Okay, second bounce ray marching. To make our physically based rendering CPB accurate, so this is the color that comes out of the of the physically based rendering, right? So you're going to get two colors here. You're going to get the color that comes out of the NERF, which is CRF, and then you're going to get the color that comes out of the physically based rendering, CPB. So these should be the same, right? Ideally, CRF and CPB would be the same exact thing, and they should both be as close as possible to CGT, which is the ground truth. We compute the rendering integral via Monte Carlo integration by marching multiple rays. So Monte Carlo here just is basically a fancy way of saying brute force, which is basically just calculated a bunch of times, and then there you go. There you have an estimate of your probability distribution. From each surface point X with stratified sampling when training. Each ray, we obtain direct illumination from the SGs and compute visibility and indirect illumination using equation 1 directly. This second bounce ray marching is known to be expensive for previous NERF-based methods, which either requires extremely high computational resources, 128 TPUs, that's fucking intense, or utilizes long offline pre-computation, which requires extra MLPs. So basically what they're saying is that other NERF papers, what they're going to do is they're going to have additional multi-layer perceptrons here just to calculate this omega I. But they don't have to do that in this paper. We instead perform second bounce ray marching, achieving higher accuracy, which is affordable thanks to our highly efficient tensor factorization representation. Yeah, so really like... and the tensor factorization-based representation is not from these guys, right? These guys are saying that they used it's TensorRF is really the paper that learned to use these density tensors and appearance tensors. But this paper added on to that by having the two separate rendering pipelines and then by using the rendering pipelines to help each other. I think that's the novelty of this paper, which I think is definitely impressive, right? I think they did succeed in kind of going beyond just what the original TensorRF paper did, or TensorF paper. Multi-light representation. We have discussed our scene representation under a single unknown lighting condition. Our method can be easily extended to support capturing onto multiple unknown lighting conditions, owing to the generality and extensibility of the tensor factorization. We achieve this by adding an additional lighting dimension with vector factors E, where the length of each vector E equals the number of lighting conditions into the factorized appearance tensor, leading to a 5D tensor that expresses scene appearance under multiple different lighting conditions. Okay, so up until now, the density tensor was 3-dimensional and the appearance tensor was 4-dimensional. But now what they're going to say is they're going to add a 5th dimension to the appearance tensor that's going to represent the fucking brain fart. That's going to represent the different lighting conditions. So as a human, it's difficult to start to visualize that, right? As a human, it's very easy to visualize a 3D tensor, right? It's just 3D space. And you can kind of visualize a 4D tensor, right? A 4D tensor is like a 3D tensor, except that for every single little point in space, you have like a vector of things, right? So if you're familiar with convolutional neural nets, like I think that's the best way to think about that, right? Like a convolutional neural net, you have a 2D image, and then for each 2D image, you have a feature vector, right? So it's kind of like a depth, right? So think about doing that exact same thing, but with a 3D tensor. So you have a 3D tensor, right, which is a volume in space. And then for each point in that 3D tensor, you have a feature vector. And then what they're saying is, okay, well, now you have that 4D tensor, and think about doing that again. So for every point in the feature vector of every point in the 3D tensor, you have another vector. So 5 dimensions is like right on the boundary of like what your human brain can even like visualize. But if you think about it kind of step by step a little bit, you can kind of visualize it in your head. Okay, we denote the 5D multi-light appearance tensor as 5DAG. So this is GA is just the 4D appearance tensor, and then G5DA is the 5D appearance tensor. And you can see here that basically the only thing they added, this is still the same. It's still a summation over K, which is the number of factorizations. It's still a summation over X, Y, Z, which are the 3 dimensions of the 3D volume of space. But now they have this additional term here, BK, right? So previously, if we scroll up, they have, or I guess it's not the BK, it's the one in between. So they have V, M, and B, right? The outer product of these 3 things. And now by adding that extra dimension, you have the outer product of these 4 things. So you actually have this EK term here now. So note that it is only the view-dependent colors that require being modeled separately under different lighting, while the physical scene properties, including volume, density, normals, and material properties, are inherently shared. Okay. So I like this. This is pretty cool. So what they're saying is that only the colors change. So the materials, the normals, and the density, those 3 things should not be impacted by lighting, right? If you change the lighting of a scene, the density of each individual point in space should be the same, right? The lighting isn't going to change that. The material properties also not going to be changed by the lighting. The what else? The normals, right? So the normal vectors, which represent the surface, also not going to be changed by lighting. So what they're saying here is that only the color, only this one here, only the radiance net here is going to be changed by the lighting. So you can see here that's why this yellow arrows here only go into the color. Therefore, we decode view-dependent color using the neural features per light and decode other shading properties using the mean features along the lighting dimension. So they're still doing this interpolation, which, I don't know. I don't know how I feel about that interpolation. It depends on kind of, like, it allows you a trade-off, right? So, like, I don't like interpolating in, like, tensors like that, but it also means that you could use a very low-dimensional density tensor and appearance tensor and save memory and compute and time, but the interpolation is not going to be as good. So, like, it allows you to trade off kind of fidelity with computation, which probably is a good thing. Okay, so what do you have here? Equation 10, where L is the light index, so you have some... See, this to me means that there's a specific amount of lights, right? So the same way here that they said they're going to use a kind of a mixture of Gaussians, to me that means that at some point they're saying there's this exact amount of lights in the scene, right? They're making an assumption on the number of lights, and L here is a light index, which means there's also some kind of assumption about the number of lights, which isn't going to necessarily be true in the real world. E is the number of lighting conditions. And A bar X is the mean feature. So the mean feature for the lighting, I guess. So A bar X is, there's L total lights. So you're summing over all the lights and you're getting the feature for that light, right? The feature AX for the light L, you're summing over all of them and then you're dividing by the number of lighting conditions P. And that gives you the average lighting feature. And the average lighting feature is going to be what comes out of your 5-dimensional appearance tensor, right? 5-dimensional appearance tensor, which is a function of a point in space, and then L, which is the light index. So those two things should be the same. And then here you have your 3 different multi-layer perceptrons. You have your color MLP, you have your normal MLP, and you have your material property MLP. Each of those, if you give them the appearance or the mean feature vector of the lighting, you will be able to get the color, the normal, and the material. So CX, NX, and then beta X. By simply adding additional vectors in the factorized appearance tensor, our method allows us to efficiently reconstruct and query the radiance under different illumination conditions, thereby still allowing for indirect illumination computation in the multi-light setting with the methods discussed in section 3. The multi-light input can provide useful photometric cues and reduce ambiguity in material prediction, therefore leads to a more accurate reconstruction of geometry and material estimation. Yeah, there's just more signal. I like this technique is just so good that because it's using all of the advantages and weaknesses of radiance based or like kind of ray marching nerf based rendering, radiance field rendering, and all the advantages and weaknesses of physically based rendering and combining them together such that they help each other. This like joint optimization process and all these little tricks that they came up with are huge. Like I think that is so important and such a great insight. Whoever came up with that, one of these authors, I don't know who came up with it, but it's fucking great. Joint reconstruction and training losses. For both single and multi-light settings, we jointly reconstruct the scene geometry and appearance properties that are modeled by our tensor factorization-based representation through an end-to-end per scene optimization. So unfortunately, that's the case for any kind of nerf, any kind of rendering technique where you're using a neural net, is that you're going to have to learn the entire static scene from scratch per scene. So anytime you see a nerf like this, like there's a set of multi-layer perceptrons specifically for this armadillo. There's a set of MLPs specifically for this hot dog. So it's a different model for every single one of these. Rendering losses. We supervise the rendered colors from both the radiance field rendering and the physically based rendering with the ground truth colors. So you have the physically based colors, you have the radiance field rendering, and then you have the ground truth colors, and then you have the L2 losses for each of those. Normal regularization, our shading normals, N, are regressed from an NLP, right? So you have an MLP, multi-layer perceptron here, that is regressing, right? Regression is just one of the basic kinds of outputs from a neural net, right? You can have classification, you can have just linear regression, logistic regression, there's different types of things, but ultimately it's like, what is the output of your neural net? In this case, it's just a vector, which is the normal. However, since the system only supervising the network output with rendering loss is prone to overfitting, use the negative direction of volume density gradients as normals for shading. Yeah, so you need to know what the actual normal direction is, right? So in these cases, right, you do have the ground truth Lego for this. So you do have the normal vectors that are ground truth. But if you try to use, if you use the ground truth normals here, you're not going to have access to that in a real world image, right? In a synthetic image like this, I know what the ground truth normals are. But in a real world image, if I went in my house and I just recorded a bunch of pictures with my cell phone, I don't know what the normal vectors are for the random video I have of my house. So you need to estimate these normal vectors. And this is what they're going to be doing to estimate the normal vectors. They're going to use the negative direction of the volume density gradients. So you see this upside down triangle here. That's basically the curl, right? Let me make sure. Curl symbol. So basically, you have this density field, and then you have some gradient along that density field, and you can basically say the kind of like the slope of that 3D thing, or the gradient, is going to give you the normal vector. Look, I just explained that in a terrible way, but hopefully you guys got it. Such derived normals are better aligned with the surface, but can be noisy and lack fine details. We correlate our shading normal with a density-derived normal using a loss. So here is a regularization term. So this is an additional loss that they use to make sure that the normal that they get from the density gradients and the normal that they get, what is NJ? I guess the normal from every single, the relighting here. But basically they want these normal directions to be as similar as possible, right? So they have an L2 loss here. This regularization term backpropagates gradients to both the appearance tensor and the density tensor, further correlating our entire scene geometry and appearance reasoning. So this is a little bit of a chicken and an egg problem. Like I said before, you don't know what the normals are initially, and you don't know what the volume density is initially. So over time, as your density tensor gets more and more accurate, right, your normal vectors get more and more accurate. And then you kind of iteratively, they refine each other, and eventually you get a much better normal vector. But it's not immediately clear to me that you would end up, that this would work every time, right? It seems like you could end up in a situation where the density field becomes worse, and then the normal vectors become worse, and then that makes the density field worse, and then it becomes this kind of like instability issue where, like, if you need a good density field to get a good normal vector, if one of those starts to become bad, then they both kind of start to become bad, right? And this kind of like training instability is an issue in other types of systems, like GAN. GANs, generative adversarial networks, are also famously very unstable and difficult to train for that reason, because the generator depends on the discriminator, and the discriminator depends on the generator. So anytime you have these two kind of like chicken and egg situations where like one thing needs to work better for the other thing to work better, and then they kind of like feed back towards each other, you can end up with instability issues. Note that while ref/nerf uses the same normal regularization, their normals are used in MLP-based shading. In contrast, or normals are used in physically based rendering, allowing for more meaningful geometry reasoning. Okay. Following TensorIF, we apply additional L1 regularization on all tensor factors, noted as LG. So they have an additional regularization loss somewhere on these density tensors and appearance tensors. We also apply a smoothness regularization on BRDF parameters beta to enhance their spatial consistency. Okay, so they have an additional loss here to this beta term here, where basically the betas should be similar in as they move around. So that's not necessarily true, right? Like let's imagine you had someone who was holding a mirror, right? If someone's holding a mirror, the material properties of their hand right next to the mirror are going to be very, very different from the material properties of the mirror. So there's kind of a discontinuity in the material properties as of like their hand to the mirror. But here, by adding a smoothness regularization, you're going to not favor that, right? So the smoothness regularization is going to favor objects that have the same material properties. So you see how here the entire object has the same material property. So different material properties for different parts of the object are going to be more difficult if you have a smoothness regularization like they have here. A loss term penalizing back-facing normals. So they have more normalization here, more regularization here. So a penalty for normals that face in the wrong direction. So they have all these extra regularization terms, which make everything nicer, and then they apply these losses to supervise and then do the whole joint optimization process. So the loss is all of this. This is the actual final loss, which is the combination of all these different losses here. You have the radiance field loss, you have the physically based rendering loss, you have the material property smoothness loss, you have the loss for the backward facing normals, you have the loss for what is LD. LD, we don't know what LD is. Okay, one of these losses, I already forgot what it is, but LD and then LG. And all these alphas here, alpha RF, alpha PB, alpha beta, these are just hyperparameters. So when you have a loss that is the weighted combination of a bunch of these other losses, you need to decide what those weights are. And usually you kind of make a good guess, make a good intuitive guess, and then optimize that hyperparameter by hand. Okay, so that's the basic technique, and now we're going to move into the experiment section, where they're going to kind of talk about the different experiments that they did and the results that they got. So let's start by looking at figure 5 here, visual comparison against baseline method. Our method produces inverse rendering results of higher quality and with more detailed normals and more accurate albedo. So we see here the this Lego, and then with 4 different techniques. So the ground truth, this is the real one, right? So they actually have a 3D model of this. Then you have nerf factor, which is a little bit of an older nerf, but it still checks out. Inverse rendering, which is also another baseline, I think also nerf based. And then theirs. And this is the part that made me want to read this paper. Like, look at this stuff here. This is literally better than the ground truth. Like, ours ground truth, like, look how much better this is than the ground truth. It's like actually better than the ground truth, which doesn't make any fucking sense. Like, how can you have something that's better than the ground truth? Right? That's fucking crazy. So it's better in terms of the crispiness, it's better in terms of like the normal map, it's better in terms of the albedo. It's just better in every single way. So here you have the environment map, right, which is like the HDRI, and you can see how the ground truth one is just like some generic HDRI, but it has a big light right here in the middle, which represents the sun. And you can see how the technique in this paper is able to somewhat reconstruct that. It's able to understand, okay, this is the environment map here has one big central light right in the middle, which is what the ground truth was. Quantitative comparisons on the synthetic dataset. Our single light results have significantly outperformed the baseline methods, producing more accurate normals and albedos, thus achieving more realistic novel view synthesis and relighting results. Our method can further take images captured under different lighting conditions and boost performance in inverse rendering. Okay. So here are different quantitative metrics of kind of quality. So you have peak signal to noise ratio, SSIM, and LPIPs. These are perceptual losses or perceptual distances. Like I think LPIPs, what it does is it feeds the images into a neural net and then compares the difference in the embedding vectors that result. So lower is better. You want less distance. PSNR, you want more signal to noise, so higher is better. So these numbers are a little bit hard to read, and like I always generally like these qualitative examples better. Like I feel like qualitatively it's much easier to get a good understanding of whether something's good than these quantitative numbers. But roughly what you're seeing here is that nerf gets about 25, this one gets about 29. And then you have some ablations here. So with rotated multi-light, with general multi-light, slightly better. And then in 25 minutes, so they limit the training time, the joint optimization process to 25 minutes. 5 hours versus 100 hours. We perform experiments on 4 complex synthetic scenes, including 3 Blender scenes and Stanford 3D scanning. We render two types of multi-light data, rotated multi-light and general multi-light. So that's the two things that they're comparing to there. We also perform experiments on the original NERF synthetic dataset. This is good. I like this. I like the fact that the NERF community has kind of decided to use this Lego kind of truck and this ficus tree. Like they've decided that, hey, that's the benchmark. Let's do it on that. We compare our model with previous state-of-the-art neural field-based inverse rendering methods, NERF factor, and inverse render. We also compare with our model trained under multi-light settings. Table 1 shows the accuracy of the estimated albedo, normal, and relighting results using PSNR, SSIM, and LPIPS. We can see that our method outperforms both previous methods significantly. Yeah, our results produce normals that are much higher quality and more faithfully reflect the geometry variations. Here they're showing you the shadows. So this is relighting. So relighting means they are adding new lights and then seeing how it interacts with the scene. So you can see how NERFs are kind of not able to deal with this because NERFs don't have a very good estimate of the normal and of the material properties, so that when you add new lighting, they don't really know how the scene is going to interact with that. Versus this technique here, the technique in this paper, it actually works very well. Like, look how crisp the edges of this shadow are. We showcase that we can achieve similar albedo by increasing the BRDF smoothness weight. Like I said, I feel like this BRDF smoothness is not necessarily a good thing because not all the BRDF material properties aren't going to be consistent across the whole object in a more complicated object. Approximates the visibility from a distilled MLP, completely ignores the indirect illumination. Both methods do inverse rendering in a second stage after pre-trained NERFs. Our tensor factorized representation achieves single-stage joint reconstruction and efficiently performs explicit second bounce ray marching for more accurate shadowing. Meanwhile, owing to our more efficient representation, our high reconstruction quality is achieved with the fastest reconstruction speed, as reflected by the reconstruction time. Inverse render is faster than NERF factor due to its sign distance function based rendering, right? Slightly different type of rendering. Our approach leverages ray marching based radiance rendering in the reconstruction, robustly producing high quality results on all testing scenes. While our method takes 5 hours to finish, we can achieve good quality in a much shorter training period of 25 minutes. Our framework can also effectively leverage the additional input in a multi-light capture and boost the accuracy of inverse rendering. So here you have the same kind of metrics for quantitative evaluation, and you see here without the visibility, without the indirect illumination, and then with the indirect illumination and the visibility, and it kind of gives you what you want here, where with both of those things together you get a better result than without. And it seems like the one that has the more effect is the indirect illumination. We compare geometry reconstruction results of our model taking only 25 minutes. So this is where instead of rendering for the full 5 hours, they render for 25 minutes, and you can see how the quality does improve. Tensor factorized representation allows us to explicitly sample secondary rays in an efficient way to account for computing lighting visibility and indirect illumination. Without including these terms, the model cannot accurately represent the secondary shading effects and tends to bake them in the albedo or normal. So here's an interesting observation, is that because other techniques aren't explicitly trying to store explicitly trying to model the secondary lighting effects, what most nerfs end up doing is they end up kind of taking the secondary lighting effects and kind of like stuffing that into the color and the radiance field, or the color and the albedo, right? The density here. Density and color, not albedo, sorry. Density and color. So the nerf has a limited representation of this 3D thing, so it doesn't have this extra capacity where it can store that secondary lighting information. So as they say here, it tends to bake them into the normal vector, which ends up resulting in a lower quality rather than having it kind of separated explicitly like they have in this paper. Okay, conclusion. So we got to the end, guys. We present a novel inverse rendering approach that achieves efficient and high quality scene reconstruction from multi-view images under unknown illumination. Our approach models a scene as both a radiance field and a physically based model with density, normals, lighting, and material properties. By jointly reconstructing both models, we achieve high-quality geometry and reflectance reconstruction, enabled photorealistic rendering and relighting. Owing to the efficiency and generality of the tensor factorized representation, which I think is really the platform upon which this work sits, the TensorRF seems really strong, but then I also think that the thing they did here with the using both physically based rendering and a radiance field rendering, I think that is very novel, and I do think they deserve credit for that. We demonstrate that our approach is able to achieve state-of-the-art inverse rendering, outperforming previous neural methods in terms of both reconstruction quality and efficiency. Pretty cool. Let's see if there's anything cool here in the abstract. So, 4 real objects we captured under natural lighting. So this is a real object that they captured under natural lighting. What they mean by that is someone sat and took pictures of this object all the way around with a cell phone. Yeah, this is still one of the problems with NERF, is that when you calculate or when you capture some pictures of something in the real world, you don't have the ground truth position of the cameras, right? So in order to estimate the ground truth position of the cameras, a lot of people use this algorithm here called CalMap, right? Which is quite old at this point. Like CalMap is an old school computer vision algorithm that's looking at basically the points that are similar between different camera angles in order to get an estimate of the camera pose. But I feel like there's an opportunity here for someone to come up with some kind of successor to CalMap, some way to get the camera position from a set of images that have an unknown camera pose. I don't know what it is, but I feel like, to me, the fact that people still use CalMap is a little bit sus. I feel like we need to move on from that as a community. Okay, quality is affected, blah, blah, blah. Here is the actual resolution of the tensors. So here, right, we were saying, what is the resolution of the density tensor and the appearance tensor? They're telling you it's 300 to the third. So there's 300 units in each dimension. The MLP, so these little multi-layer perceptrons here, the normal net, the material net, and the radiance net, they're 2 layers, so still very tiny multi-layer perceptrons, 128 channels, which basically just means the size of the fully connected layers, and ReLU activation. So this is a very simple little MLP. Here you have more precise. Here's the actual GPU. So they're running this on a single RTX 2080 Ti with 11 gigabytes of memory for all our results. That is very achievable. Damn, this makes this paper so much more impressive, because even the GPU in this computer is better than that. So I like that. It's very impressive. Atom optimizer, of course. Initial learning rates of 0.02, 0.001. They upsample the tensors, total amount of 80,000 steps of training. The training ray batch size. So when you're doing a nerf and you're training a nerf, you're basically calculating these rays, and then you have ray bundles, sometimes they're called, but basically a batch of rays. And yeah, the size of your model plus the total amount of your rays, right, the size of your batch needs to be less than the amount of memory on your GPU. So if you have 11 gigabytes of memory on an RTX 2080, they say that the maximum batch size for the number of rays is 1024. Do some fancy detaching in order to save on GPU memory. The secondary ray sample, which is the indirect lighting, is coarser than the primary ray sampling. Sense that's kind of cool. So basically, this D, right, this green D vector here, which represents the primary camera ray, is going to be sampled. Here it shows with 5 points, and we don't know what the sampling is for the indirect lighting, but they're saying that the sampling is lower. This is the BRDF smoothness term, and then the back-facing normal term. So these are the two regularization losses. Lots of different little tricks here. I like how they tell you everything too. So they have L1 regularization on tensor factors, which means that they have an additional loss that prevents the individual terms inside those tensors from getting too big. So, right, you basically don't want individual numbers in there to get really, really huge. Prevents any single part of that tensor factorization from dominating. Comparison of single light and multi-light. So finally they give us the number. So there's 3 lights in the multi-light case. What else do we got here? Reconstructed environment map, so showing you that the ground truth has like this central lighting, and then the actual reconstructed map is actually pretty accurate. You see here how it understands that this is where the light comes from. This is where the light comes from here. It actually quite matches. And then you got some results. This looks fucking amazing. These relightings are so good. Look at that. This is the general, and then this is the ground truth. Like, it's like I keep saying this, but I feel like it's literally better than the ground truth, which is insane. Pretty cool. Look at this drum set. This drum set and then this little like pirate ship are also from the original Nerf paper. Cool. So that's it for this paper. Maybe just to summarize what's going on here. So basically, this is a paper that comes out of Adobe Research and a couple different universities here. You see a little bit of a competition going on where you have equal advisory, equal contribution, and equal advisory. So people are fighting over who gets credit on this work. So you have people from this university and UC San Diego kind of fighting over this, which is interesting. It tells you that there's something to fight over. The main novelty here is that they're using both physically based rendering and radiance field rendering in order to get a more rich loss and gradient signal, right? So in a lot of NERF papers, this whole part down here would just be removed and you would basically be only feeding gradients from the radiance field rendering. But here they used both the physically based rendering and the radiance field rendering together, and they had all these different little tricks, such as using the radiance field rendering to calculate the secondary illumination bounces, which was pretty crazy. So in terms of the density tensor and the appearance tensor, that's not unique to this paper. That's from the TensorRF paper, but they do kind of expand on that. So I feel like they did well. Where does this go in the future? I feel like this to me almost replaces NERF, right? Like why not use this more richer loss when you're doing your NERF stuff? And then here's the even crazier thing, right? What if you take this and here, right, condition the density tensor and the appearance tensor on a guidance weight, right? So in stable diffusion, right, stable diffusion model guidance vector, right, you're feeding a vector that represents the thing that you want, right, like the actual object, right, like a cat, or that's where you put the text in, right? So you're using, let me see if I can find a good picture, but you're taking your text, converting that into a text embedding vector, and then conditioning your generation based on that text embedding, right? With a guidance weight. You could do that same exact thing here, right? You could condition this entire pipeline on a guidance weight coming from a clip model, right? And we've seen that before. We've seen people do kind of like text-guided NERFs, but I haven't seen anybody do a text-guided NERF that uses this tensor factorization and these two parts here. So that seems like a really awesome next potential step for this research direction. And then also another step that they could take, especially since this is coming from Adobe and Adobe has a bunch of money, is train a bigger version of this, right? The multi-layer perceptrons that you're using are very small. Train a much bigger multi-layer perceptron, train it on lots of different scenes and objects, and see if you can get some kind of foundational NERF model, right? And then take that foundational NERF model, distill it, and then put that on a VR headset. And I feel like that's it. I feel like that's literally the only things you need, and then we will have a full reality in a VR headset that's rendered real time that you can describe with a text. We're so close. We're literally less than 5 years away from you put on a VR headset and you just start talking and it just starts rendering and you can create your own universe. Less than 5 years away, guys. We're almost there. Cool. Hope you guys found that useful. Let me know if there's other papers you want to read. There's a shit ton of CVPR papers out. Too many to actually read, but if you guys have good recommendations on cool computer vision papers, let me know. Join the Discord and feel free to ask questions. If not, have a great day. Talk to you guys later.